So in this installment, we're going to talk specifically about this stationary friction. Stationary friction, or static friction as we should call it. Stationary means static friction. And the definition of the coefficient of static friction is it's the ratio of the force of friction to the force normal. And it has a label, mu. This is the Greek letter mu, the same as mu m micrometer. And it's pronounced mu, Greek letter mu. And we say it's mu s for mu static. It's the ratio of the force of friction to the force normal. And why that should be is illustrated in this diagram over here at the right. If we take two surfaces, even up close if they seem fairly smooth, there are some imperfections in those surfaces. And so then if you wanted to pull this to the right, well, as you tried to drag it, the resistance would come because of the intercalation of these teeth or these jags. And you could see then if you increase the normal force that those intercalations would be harder. They'd be pushed down in there further. And so it probably stands to reason to you that it would take an even bigger force when the normal force is larger. Another way, we can take this ratio of mu s and rewrite this equation so that such that force of friction is mu times the force normal. And in this form, we can see in this relationship that if we double the force normal, we will double the force of friction. Increasing the force normal will increase the friction. And this mu s is unique to every pairing of materials. Now we might look at this a little closer and say, well, what would it take for this mu to be 0? Well, for the mu to be equal to 0, the force of friction would have to be 0. Oh, so a mu of 0 would be something very, very slippery. No friction. And what about a mu s equal to 1? Well, then you could see is that the force of friction would have to be equal to the force normal. And we know in this particular case over here, if an object is sitting on top of each other, that we have the force of gravity and we have the force normal being equal and opposite to each other. So to have a mu of 1, the force would have to be equal to the weight. In other words, the force would have to be so large that we would have to lift it upward. The force so large it could lift one off of the surface. Now, if you think about that, lifting it off the surface, well, lifting it off the surface means you'd be pulling the teeth out. And that's exactly what's going on, providing a force so large that it can actually cause the material to raise up. And that's what's going on when something is stationary. To get it to move, this does have to move upward. This little point right here, to keep going, has to get up above this or be broken off to be able to slide. So fundamentally, to break that stationariness, you have to raise it up so those surfaces can slide past each other. So that force has to be large enough to lift it vertically. So to start sliding, the surface has to be raised high enough so the jagged edges can rise up and over. Thus, force applied equals Fg. And that's the most it would ever be when there's a coefficient of 1. Now, of course, if the force were higher than that, were greater than gravity, then it would definitely easily pick it up. And so that's why mu's must range between 0 and 1. The minimum value of all mu's is 0, and the maximum value is 1. Now, you may wonder about this. Well, if this is really about the weight, why isn't this equation here FF to FG? And it turns out it could be if it were horizontal. But if we now take those two materials and we put them at an angle, you can see now that the normal force is like this, and the gravitational force is oriented this way. And so gravity isn't pulling these into each other as hard as when they're horizontal. We know that in an inclined plane, the normal force equals the weight when it's 0 degrees, but as we increase that angle, the normal force decreases and decreases to 0. Well, what friction is necessary if you have a vertical wall and you put an object on it and let go of it? What force is necessary to overcome friction? The answer is 0, because the normal force is 0. Force of gravity stays the same the entire time. And so you can see then that the force of friction isn't related directly to gravity. It's related to the normal force. And as we increase this angle, the normal force decreases. So a couple takeaways here. We have this definition of mu, the coefficient of friction, which is mu s. It's the ratio of the force of friction to the force normal, and that's the force of friction static, to the force normal. And we can rearrange this equation so it's a linear equation where the force of friction is a product of these two. And in which case you can see if you increase the normal, you'll increase the friction. Or if you increase this ratio, you'll increase the friction. And that is the coefficient of static friction. That coefficient of static friction, of course, pertains to the data we obtained here. And the static friction is here. And so the maximum force we achieved was 7.164. And so to do the computation here, we would say mu s is the force of friction static maximum over the force normal. So that would be 7.164 newtons. And whatever the force normal was of that cart, of the basket. And if I told you the basket was 15.246 newtons, then we could do a simple calculation. And that ratio would work out to be equal to 0.46989. And since it's newtons over newtons, there's no units, no dimensions at all. So the mu static would be 0.46989, no units. And then to use the significant digits, we would have 4. So that would be 0.4699 would be the mu static for that particular scenario, where the weight of the crate is 15.246 newtons, and our max force was 7.164. Now again, since the crate is on the ground, force of gravity and force normal are equal and opposite to each other. So we did use the weight, 15.246, for the force normal.